right, excellent. Okay, before we begin the discussion on the contents of our lecture today, just a couple of reminders. The quiz 1 has already been opened, eh? I've seen the latest update, there were 18 who have attempted already. But you have this week in which to attempt quiz 1. You have a maximum of 2 attempts to do that. It will close on Sunday, midnight Sunday. Second announcement is test 1 is in week 7. So sometime this week or early next week, then I will send you the test format. Test format gives you an idea of the types of questions that you will anticipate in test 1. And I will also give you some information of when in week 7, what day and what time, and the venue of the test also. That has not been confirmed. Once that information is available, then I'll let you know. And thirdly, by end of this week, or early next week, we'll send out a list of non-starters. A non-starters list gives you information on those students who have registered in the course in Lothala but have not attended any tutorial. So keep a lookout. If once that is sent out and you know of anyone in the list, any of your friends in the list, just let them know that they need to attend the tutorials because that's important. Usually those whose names are in the list of non-starters, they usually fail the course because it's important that you attend the tutorials as well as the lectures. I think by, if not end of this week, early next week, we'll set up a tutorial attendance sheet in Moodle where you should be able to view how many tutorials you've attended. We'll try and update that every week. So at the end of each week, we'll update a tutorial attendance sheet in Moodle. So you know how many tutorials you've attended in the semester. And if you have issues with the tutorial attendance, send us an email so we can cross-check with attendance sheets that you normally fill at the end of every tutorial. So that's for Lothala students. Okay, for today's lecture and the coverage for this week, let's see. Just quickly. All right. Today's coverage. This week's coverage will include the discussion on the domain and range. This is part of Course Book 1, Unit 2. We'll start off with functions and graphs. And we'll work on functions first. We'll be discussing domain and range, and addition and subtraction or multiplication of two functions and identifying their domains and range. And by, when is our next lecture? Wednesday, we'll discuss composite functions and their domains and range, and inverse functions as well. And those are part of the discussion in the tutorials this week as well. Now, if, let me have a look. Week 4 tutorial. Determining domain and range, and combination of functions, addition, subtraction of functions, and we'll also be doing some composite functions. But I think for some tutorial sessions, they will still be doing mathematical induction. That's fine. Okay? If your tutorial session is still on mathematical induction, that's okay. But I expect this to be our lecture coverage. What is this? So let's have a look at the PowerPoint slides. We'll first work on functions, and as I had said, we'll begin with the discussion of domain and range. These definitions are in your course book, so let me just re-emphasize them again. We talk about mathematical expressions or some mathematical relations, a relation between two variables. One is independent and the other is dependent on the other variable. And a function is a rule that assigns one element, a domain, to another element, the range. And the function that relates them, we're giving it a mathematical notation f or g or even h, assigns a value to exactly one and only one y value. Now, as I had said, there are mathematical relations. We have mathematical equations. Not all mathematical relations are classified as functions. A mathematical relation, it becomes a function when we assign to every x value exactly one and only one y value. So, in your course book, there are a number of the checks that we can use to determine whether a mathematical expression is a function or not. Your course book uses the vertical line test. In a vertical line test, once you have a mathematical expression in the form of a graph, what we do is we drop a vertical line through the graph. As in this case, the mathematical expression becomes a function if you drop a vertical line through the graph and the vertical line passes at only one point. So as in this case, if I drop a vertical line, How many points does the vertical line cut the graph? At only one and only one. So this is an example of a mathematical expression that is a function. So that mathematical expression, we can now classify it as a function. What happens if, in this case, if you drop a vertical line, how many points does the vertical line cut the graph? At 2. This is an example of a mathematical expression that is not a function, because it cuts at more than 1 point. And this type of graph is the graph of square root functions. However, we can change it, the graph, to become, even though it is still a square root graph, we can still change it so that it cuts at only 1 point. What we do, we'll remove part of the graph, the bottom part or even the top part of the graph. So if we remove the bottom part, let me see, there you go. It's still a square root graph, but we've dismissed the lower half of it. And this now makes this relation a mathematical function. So we'll have a look at some of these later on. Like I said, this is an example of a square root function. Okay, domain and range. We will begin by having a look at the domains and range of polynomials. Domain is all the values that go into a function. Some prefer to describe the domain as the set of first elements in a relation. And the range is the set of second elements in a relation. As in this case, that's the function. So the x values are domains, and the result of substituting the x value into the function is the range. For me, I prefer to identify domain, if I can just describe it how I like to describe it. Domain elements, a mathematical relation, set of first elements. And so the range becomes set of mathematical. So the range becomes the set of second elements in a relation. So we've specifically allocated domain, set of first elements that you will substitute. And usually the domains are independent values that you enter. The range are dependent on the domains and the relation that we're using. So that's some explanations on domains and range. So if a function is x squared, and we've set the domain as 1, 2, 3, what will the range be? We are substituting it into the relation. One, 4, 9, and so on. So domain and the range. So we can identify the domain by the equation that is used or the function that is used or even the graph. Now, this is important because usually the domains can easily be identified, but it's the range that we will have to somehow work out a system of identifying the range. And it's usually easy to identify both the domain and range if the relation is in graphical form, as in this case. So if I am to ask you, determine the domain, all you need to do is to describe what values of x we are using. So what are our x values here? You'll just need to describe these x values. If I say this is 2 and this is 4, the domains are x values between 2 and 4. And as you can see, they are all parts of real numbers. If I am to describe the range, I describe the values that represent the y values that are represented on the graph. So there are two things we can, for now, two things we can do to describe the domain and range. You can either use the equation or use the graph. Let's have a look at some examples. (2x minus 3). What type of function is this? Linear. I'm hoping you can draw the graph of linear. Now notice, for this linear graph, there is already a domain given. What's the domain of this linear graph? X values we're using are less than -1, and they are all real numbers. This is an example of a function that has restrictions. The domain has already been restricted for us. So the domain, x is an element of real numbers. And then you will have to decide what the range will be. If I substitute -1 into the equation, what y value will I get? 2 times -1, -2, -1, -5, yeah. And that should help you describe the range. Or it would be best for you to draw the graph. Y equals 3x. What type of function is this? Sorry. Again, linear. We can use any x value. Substitute an x value here, you will always get a y value. If I substitute 100, I'll get a y value. If I substitute -100, I'll still get a y value. So how do you describe the x values? All x values. Or mathematically, yeah, all x values, sorry. Mathematically, x is an element of real numbers. Now here, because the domain is already restricted, we can only use these x values. So let's start off with linear, quadratic, and cubic, or polynomials generally. This equation is given in your course book. All right, let's start with linear functions that have no restrictions. Again, by now I'm hoping you understand linear functions that have restriction. This is an example of one. Now let's have a look at linear functions that have no restrictions. Domain will always be x is an element of real numbers, and the range will also be y is an element of real numbers. Because for whatever linear function given without restriction, you can use any x value. And if you substitute any x value to that linear equation, you'll always get a y value. Quadratics without restriction. How do we know that a function is quadratic? I think we've mentioned this. It has degree 2. Domain X is an element of real numbers. However, the range of quadratics depends on the function used. For example, x squared minus 2. Domain X is an element of real numbers. The suggestion is that it's best that we use the graph, the graphical method, to try and describe the range. So let's have a look at, by observing, if I substitute any x value here, if I substitute negative 100 or positive 100, or if I substitute 0. If I substitute 0 here, what y value will I get? Negative 2? If you substitute any other x value, the lowest y value you ever get is negative 2. Or, if we use graph, let's have a look at the graph of y equals x squared minus 2. Okay. If the graph is given, how would you describe the x values? I would prefer to have arrowhead. That means the graph continues indefinitely in both sides. So, is this x value used? I draw a vertical line, it cuts the graph. So that means this x value is used by the graph. How about this x value? Draw a vertical line, does it cut the graph? Yes, so that means this x value is used. Is this x value used? Draw a vertical line. Does it cut the graph? Yes, so that means this x value is used. Is this x value used? Draw a vertical line. Remember, the graph extends indefinitely, so that means this vertical line will also cut the graph, meaning this x value is used. So if you have a look, this graph uses all x values. How do you describe that mathematically? X is an element of real numbers. Now let's try and describe the y values, the range. For the range, I would suggest that we draw horizontal lines. Okay. Question is this y value used? Draw a horizontal line. Oh, it actually cuts in two places. That confirms that this y value is used. Agree? This y value, is it used? Draw a horizontal line. Yes, it is. Okay, this y value is used. This y value, yes, it is used. This y value, negative 2, it is used because the graph is already on. How about this y value? No. So it looks like this graph uses y value from negative 2 and above. So how do you describe those y values mathematically? Y is greater than or equal to negative 2, because negative 2 is also used. And y is an element of real numbers. So apart from observing the equation, I would prefer that we use the graph, if you can quickly draw the graph. So how about the domain of x squared plus 1? What's the shape of x squared plus 1? Quadratic. Domain X is an element of real numbers. If you use vertical lines, how would you describe the range? Y is greater than or equal to positive 1, because we are using, the graph uses all of these y values. So this is x squared. Okay, how about negative x squared plus 1. What's the shape of negative x squared? It's an inverted quadratic graph, and plus 1 means we're moving the graph up 1 unit. So let me draw the graph. Sorry. There. Domain. X is an element of real numbers. Range. Y is? Yes, absolutely. Less than or equal to 1, because we're using these y values down here. So again, I prefer that you use the graph. If you can quickly sketch the graph doesn't have to be exact. But if you have an idea on how to sketch the graphs, that would really help you out. All right, let's move on. Cubics without restrictions. Again, domain is x is an element of real numbers. Range, y is an element of real numbers. An example, y equals x cubed minus 4x. That's the graph of y equals x cubed minus 4x. Okay. Determining the domain. Is this x value used? Draw a vertical line. Remember, the graph extends indefinitely down. So that means if you draw a vertical line here, it will definitely cut the graph. I was going to say cut the grass. Fire. So that means this x value is used, eh? How about this x value? Draw a vertical line, cuts the graph. So that means this x value is used. This x value, yes. This x value, yes. So it looks like we're using all x values. How do you describe that mathematically? X is an element of real numbers. Okay, range. Y values. Are we using this y value? Horizontal line. Yes, because it cuts. So that means we're using this y value. This y value? Yes or no? Yeah. Even though it doesn't cut this side, if you set it across, it cuts this graph. So that means this y value is also used. This y value? Some need to use my glass. Yes, we can, eh? Right, lovely. This y value? Yes, because, so looks like again we are using all y values. How do you describe that mathematically? Y is an element of real numbers. Okay. Oh. So that's with cubic graphs. Now, if the domain is already restricted, then that will affect the range. We move on to square root. Remember the graph that we had discussed before, that where we use the vertical line? That's an example of a square root graph. So, to determine the domain of square root graph, it's in your course book. Let me just describe it. The easiest way of determining the domain of the square root is if we let the expression inside the square root be greater than or equal to 0. Let me mention that, state that again. Expression inside the square root is greater than or equal to 0. So you will have to identify which expression is inside the square root so that you can make it equal to, greater than or equal to 0. And as in this case, what's the expression inside the square root? a2x plus a3. We will, to determine the domain, we will make this greater than or equal to 0 and rearrange it. Take a3 to the other side, it becomes negative a3, and then we will remove the a2. So that will determine the domain of square root graphs. So let's have a look at it. And again, the range, I would suggest that you sketch. Sketch the graph if you can. I don't want us to spend too much time sketching square root graphs because I'm assuming that you know how to sketch. I don't like that word. Okay, here. What did I do? What? Wow. You want to see their faces, man. Okay, here. Domain of square root x. What? Man. Okay. Try again. The basic, let me see. Basic square root graph. That's the graph of square root of x. Now, because we are now focusing on functions, in order for this to become a function, we'll remove this part of the graph. So now, when we talk about square root x, that's the graph of square root x. We have removed part of the graph. So we ask ourselves again, is this x value used? No. Is this x value used? Yes. This x value used? Yes. So that means we will be using x values from 0 above. And how do you describe that? X is greater than or equal to 0. And please make sure you attach x as an element of real numbers. Oh yeah, the range. Oh, I've got y is greater than or equal to. Are we using this y value? Yes, we are. We're using this y value, and again, the graph extends indefinitely. So we'll be using the y values from 0 and above. That's why we have called it y is greater than or equal to 0. So let's have a look at square root of x plus 2. Domain. We said to determine the domain, What was the explanation given? Expression inside the square root is greater than or equal to 0. What's the expression inside the square root? X plus 2 greater than or equal to 0. Then you'll have to rearrange it. So domain, x is greater than or equal to -2, and x is an element of real numbers. And to determine the range, again, I would suggest that you sketch the graph. Yes, something that you need to know. Remember what we said, that the square root graph looks something like this. Square root x. If you have a +2 inside the square root, what happens to the graph? Which direction does the graph shift? It shifts to the left. So if it was a -2 in here, it would shift to the right. So, domain, is this x value used? Yes. X value used? Yes. This x value? No, so it looks like we're using x values -2 and above. How would you describe the range? Y values, we're using this y value, and we're using y values 0 and above. Y is greater than or equal to 0, an element of real numbers. Now, how about this example? Square root of 4x plus 5, there's a -1 outside of the square root. How do we determine the domain? Expression inside greater than or equal to 0. 4x plus 5 greater than or equal to 0. Domain. All right, can you just work out the domain of this square root function? Work out the domain of square root of x minus 2 plus 3. Domain, quickly. X is greater than or equal to +2. Because we will just be focusing on what's inside. Now the range. How would you describe the range? Now that we have the graph. What y values are we using? We're using this y value, -1. Are we using 0? Yes. Are we using 1? So how do you describe the range in this case? Y is greater than or equal to -1. Then we move on to rational functions. There are two types of rational functions, or two forms of rational functions that we'll be using. One uses ax plus b over cx plus d, or the other one, a over x plus b, everything plus c. So if it's one of the two forms, how do we determine the domain and range? Now notice, these two functions are defined only if the denominator is not equal to 0. Because we know that any number divided by 0 is undefined. By the way, give me a real-life situation that uses divided by 0. Real-life situation that uses divided by 0. Okay, hold on. Real-life situation that uses divided by 2. You divide a loaf of bread between two people. Yeah, then a real-life situation where you use divided by 0. Okay, pause. Real life situation where you have 0 divided by 4. Calculate 0 divided by 4. Before you finish again. 0 divided by 4 is 0. Now, if you do not understand where that is applied, then what's the use of us discussing this? Real life situation where you use 0 divided by 4. See? 0 divided by 4. Yeah, give me an example of a real life situation where you have 0 divided by 4. Divide no bread between 4 people. How much does one person get? 0, Wele. Now let's change that around. How about 4 divided by 0? Your calculator gives you undefined. Give me a real life situation that applies that. Absolutely. 4 loaves of bread divided by nobody. It's undefined because it is meaningless. Okay, in rational functions are defined only if the denominator is not 0. Because if the denominator is 0, now we know it's undefined. And this also describes the domains. The domain of all rational functions if the denominator is not equal to 0. Because once it's equal to 0, then... So in the first type, the denominator is cx plus d. If we rearrange this, move the d, move the c across. What do you get? That defines the denominator, the domain, sorry. X is not equal to negative d over c. That's type 1. If it's type 2, denominator is not equal to 0. X plus b is not equal to 0. X is not equal to negative. But please, once you've done that, attach. X is an element of real numbers. That is important. And then the range. Type 1, if you sketch rational graphs, what is peculiar about rational graphs is that they use the asymptotes, the horizontal and the vertical asymptote. And the horizontal asymptote in this case is obtained by dividing the coefficient of x, the numerator and denominator. Or if it's type 2, coefficient of x. If it's type 2, the range, again, horizontal asymptote is obtained by the plus c value. So, range y is not equal to c, an element of real numbers. Domain, denominator not equal to 0. 4x minus 2 not equal to 0. Rearrange that. X is not equal to, is it not equal to 2? I don't think so. Yeah, half. An element of real numbers. And range, yeah, range we will be using dividing the coefficient of x in the numerator and denominator. If it's of type 2, domain, denominator not equal to 0, x minus 2 not equal to 0, so domain becomes x is not equal to 2 and element of real numbers, the range is plus c. Y is not equal to 1, an element of real numbers. Constructions of functions requires that you add or subtract or multiply functions. Once you've done that, then you'll also have to describe the domain and range of combinations of functions. If we add or subtract two functions, as in this case, x squared and gx, we'll just add the equation straight away. The domain of x squared is element of real numbers. Can anyone tell me what the domain of gx is? X is, the expression inside greater than or equal to 0. X minus 1 greater than or equal to 0, so x is greater than or equal to 1. So if we add the two, we'll add them straight away, x squared plus square root of x minus 1. Now, issue here is domain. How do you identify the domain of this combination? You will have to intersect their domains. Now, domain of x, element of real numbers. Domain of f is x, element of real numbers. Domain of g, x is greater than or equal to 1. If we draw a number line, intersection, that's x is an element of real numbers. Yeah? And domain of g, x is greater than or equal to 1. Now, which region is common between the two? Or which part of the number line is common between the two? It will just be this part. That's the common region between the two. So that will describe the domain. X is greater than or equal to 1. And the range will require that you draw their graphs. Let me try this out. Give you an example. Fx is equal to x plus 1 minus 2, and gx is equal to minus 2, they call this minus 2. Gx is equal to x plus 3. Okay, we've got fx and gx. I want you to give me the expression, the equation of f minus gx.